Hey everyone, we're going to take a minute here to look at the math involved when we're dealing with uniform circular motion. Like we did linearly, we're going to talk first about velocity. If you remember going back to linear motion, first thing we talked about was velocity, then we talked about acceleration. We're going to do the same thing here. We're going to start talking about the velocity. Keep in mind that the term uniform circular motion, by definition, means moving in a circle at a constant speed. That constant speed, that's really what we're looking for here. We want to figure out what that constant speed is when we're traveling in a circle. In order to do that, we're going to think about what it is that we're actually measuring. Right? When we want to talk about we call it the velocity, but really we're calculating the magnitude portion of that velocity, which is why we're going to calculate it as a speed. If you think about moving in a circle, if we start and end at the same spot, technically our displacement would be zero, our velocity is zero, but that's not what we're looking for, right? We're looking for that uniform circular motion. We're looking for that constant speed, right? So we're going to say the velocity because the direction does matter. We're traveling in a circle. But when we're looking for just the magnitude of it, we're looking for the speed. In order to do that, if you remember linearly, we're talking about distance divided by time. Well, if I'm talking about one lap around a circle, what is it that I'm actually looking for? One lap around the circle is the circumference. Well, how do I calculate the circumference of a circle? The circumference of any circle is just 2 pi r, and divided by the time gives me the velocity. Now, when we're traveling in a circle, when we complete one lap, we actually can also call that one cycle as far as completing a circle. The amount of time it takes to complete one cycle actually has a very special name. We call that the period. And we give that a special T, right? We give it a capital letter T so that we can distinguish between just a general time or the amount of time it takes to complete one cycle, which means my equation for calculating the speed of traveling around a circle is really just going to be 2 pi r divided by the period. That gives me my velocity. Now, what I want to do is I want to look at that a little bit and talk about the moving around of a circle. And let's imagine that this circle that I have drawn here, let's imagine that this is, say, a record. Like we saw the washer on a record player as part of your lab. And I want to, instead of looking at one washer on the record player, we're going to put two. Let's say I have one here that's a little bit closer to the center, and then I have a second one that's a little bit farther out from the center. And if we think about the amount of time it takes for these two objects to go, because the record is a solid piece of material, these two objects are going to complete their cycle in the same amount of time. Let's get that on there. And let's make our red circle here to show the amount. Oops. Right, and if we look at those, they didn't end up perfectly centered anymore, but that's okay. If we look at the amount of coverage, the amount of distance that each object has to cover, look at the circle, look at the blue circle that's covered compared to the red circle. Yet we know that because they are on one piece, or they are on one solid piece, one record, that as they go around, both of them will come back to the same position at the same amount of time. What that tells us is if you're on the outer end of a circle, imagine being on the far outside horse of a carousel, or in this case, a penny that's farther outside on the record than, say, the red circle that's a little closer to the inside. Linearly, you have to be moving faster. And that goes along with our math too, right? If we think about what we have going on here, if I'm looking at the red penny, the velocity would be equal to 2 times pi times a little r divided by the period, or the amount of time it takes to complete one cycle. When I look at my my blue velocity, it's still 2 times pi, but now times a bigger r, but the time is the same, right? If I think about, as my radius goes up, my velocity has to go up. If my radius goes down, my velocity has to go down. It's one of those, it's why we like being on the inside of a track, because in order to keep up with the person, if I'm farther out, I have to go faster in order to keep up with the person that's on the inside, because I have more distance to cover, right? It's why when you run the mile in gym class, you don't run it in the outside lane, you run it in the inside lane. It gives you less distance that you have to cover, right? So there's a little bit about the velocity, right? What we're looking for is the amount of time it takes to complete one cycle, right? That amount of time would be the period. The one cycle is the 2 pi r, and that is how we calculate the velocity of an object in uniform circular motion. Thinking back to linearly now, the next thing that we did was we covered the acceleration, right? And you guys should have done a worksheet in your packet that dealt with the centripetal acceleration. But I want you to think about, let's move our circle back here, right? The acceleration of any object that's traveling in a circle, there's two things that are happening here. We're changing direction, or we can also change our speed, right? That's how we accelerate, change our direction, change our speed. Well, we're always going to be changing our direction, right? So now we want to ask ourselves, when I'm dealing with a centripetal acceleration, what's going to play a factor in how much I'm actually accelerating, right? How much is my velocity changing? Well, there's two ways that I can change my velocity. I can change the rate at which I turn, or I can change my speed going around any individual circle. And I want you to think about this red circle compared to this blue circle. The red circle, if I'm looking at it, I'm changing my velocity quite rapidly, right? I'm moving around the circle, my direction's changing really rapidly compared to my blue circle, that my velocity doesn't change as quickly, or my direction doesn't change, I should say, as quickly as the red circle, which means that as I get a bigger radius, my acceleration actually goes down. Right, the larger radius I have, the less accelerating I'm doing, provided I'm traveling at the same speed, because my direction doesn't change as much. Because of that, I get an inverse relationship, which means when I'm going to do my calculation, my radius is actually going to be on the bottom of any equation. The other way that I can look at it is if I only have one size circle, let's take like the rim of the black circle, for example. The other way that I can accelerate more, or I can change my velocity more, would be to go around the circle faster. I'll change my direction more, I'll accelerate more as I'm traveling around. Ultimately, it's not just a relationship of v, but it's v squared. So my acceleration, my centripetal acceleration, my center-seeking acceleration is equal to v squared over r. For any object that's traveling in a circle, I can calculate that acceleration by using v squared over r. And if we think about our circle, let's go back to just creating a circle that we can draw on here. That was not what I meant to happen here. Let's try that again. There we go. If I look at any spot that I'm at, if I want to look at the velocity the velocity is always tangent to the circle. So anywhere that I'm going, my velocity is always straight tangent to the circle. So when I'm trying to change my velocity, again, going back to calculating that acceleration, I can change it by moving faster around the same one circle, or by changing my direction at a higher pace. That happens with the inner circle. That's why it's the v squared over r. For any acceleration, remember we talked about the centripetal acceleration, or the center seeking. That is pointed towards the middle. And why is my acceleration pointed towards the middle? Well, because my overall net force is pointed towards the middle. If I'm dealing with acceleration and force, one of the things that I can do is go back to Newton's second law and think about how I can calculate my acceleration, or what's related to my acceleration. And just like it was before, that is equal to my F net over m. Right? That doesn't change. But now what's my net force? Because it's a net force that's causing me to move in a circle, I can call that a centripetal force, or we can say it's equal to the centripetal force over the m. Remember, that's a net force. There's not just a magic centripetal out there that makes me move in a circle, right? It's the net force. It's, the combination of any two forces that are pointing towards the middle, or two forces, if one of them's pointing away, it's still big minus little, right? It's the net force that's pointing towards the middle. So if I want to calculate my centripetal force, that is, or my centripetal acceleration, that is still my centripetal force over my mass. Rearranged, for force, that would be F sub c is equal to m times A sub c. And using our A sub c equation, we can rewrite that as F sub c is equal to mv squared over r. And that's typically how you'll see things written out for calculating what the centripetal force would be, as mv squared over r. Okay, your next video is going to have Mrs. Fine Ice taking you through solving a couple of problems. Enjoy your day, take care of yourselves, and we shall see you tomorrow.